Hi, I'm Attila.
I'm Julia.
I'm Tristan.
Keen.
And today we're going to be looking at a two-stage pressure regulator, which reduces gas pressure in two stages using a diaphragm mechanism. Looking at the parts, we have an outlet low pressure gauge, a high pressure inlet gauge, a pressure adjustment handle, an inlet tube, a relief valve, and not pictured is the factory adjustment and the outlet tube. Looking at the flow path for this pressure regulator, we have flow coming in from a pressurized gas container, flowing past the high pressure gauge, which shows the inlet pressure. The flow goes into the first stage diaphragm, which reduces the pressure initially. This flows past the relief valve and then into a second stage diaphragm, which is adjustable, which drops the pressure once more until the outlet. The working principle for this pressure regulator is a force balance between the diaphragm spring and the pressure force from the gas in the chamber on the diaphragm. The spring extension is manipulated to change the pressure required in the chamber to close the valve. If the chamber pressure is low, for example, the stem valve will be open and gas will flow in until pressure increases to the desired amount.
We're making a few assumptions to analyze the system. First, we're assuming that the spring and normal forces are all conservative. We are also assuming that the flow is Reynolds and time average flow, which will allow us to conduct our analysis and neglect turbulence. And we also assume a large Reynolds number, which allows us to ignore viscous effects and apply conservation of momentum. All assumptions for gas type and operating pressures come from Victor VTS 2534 documentation. These are the required parameters for our analysis. The pressures are specified by the documentation mentioned before. The spring constants and displacements are defined in order to conduct force balances. The first part of our analysis is an equilibrium on the first stage diaphragm. There are four forces acting on the diaphragm. There's a spring force and an atmospheric pressure force acting downward on the diaphragm, and a normal force from the stem valve and the pressure force from the chamber acting upward. This force balance will allow us to determine the pressure in the chamber from these parameters and continue the analysis. The second part of our analysis deals with the second stage diaphragm. This analysis is almost identical to the analysis of the first, except the distance x2 is now changeable.
For our new system parameters, the values listed are either based on the previously mentioned documentation or hand measured from the regulator itself. Conducting a mathematical analysis, we can use the integral conservation of momentum equation to solve for the outlet velocity in terms of the other parameters. Additionally, we can calculate the speed of sound in the carbon dioxide gas and combine this with the outlet speed to calculate the Mach number. For this device, the Mach number is just above the compressibility limit, but this will not impact our analysis. Analyzing the mass flow rate, we can assume that conservation of momentum is satisfied. Using the equation above, you can see that the maximum mass flow rate is a function of the density, pressures, and areas of the inlet and outlet.
Now delving into how parameters can change the effect of the system, we see that tightening the diaphragm knob can increase the spring force, which would increase the pressure inside the regulator. A larger spring constant results in a larger spring force magnitude, which would also increase the pressure inside the regulator. To achieve a higher achieved pressure, we can stiffen the diaphragm spring, compress the diaphragm spring, or decrease the diaphragm size. We can also do the opposite with the stem, but this is much less desired. In terms of changing the diaphragm area, an increase in the diaphragm area causes an increase in the force that's going to be exerted by the gaseous pressure, which also leads to a decreased achieved pressure. Increasing the inlet pressure causes an increase in the outlet velocity, which also increases the mass flow rate as shown in the equations below. And changing the desired mass flow rate can lead to an increased outlet velocity if we were to increase the mass flow rate, and vice versa. It's important to note that this particular valve has a maximum operating pressure of 3,000 psi. So to increase flow rate further, a different valve will be needed, one that is either larger or stronger in order to withstand higher pressures. And these are our citations. Any questions?